viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am an associate professor in the Department of Computer Science, Aribhat College, University of Delhi. So our current series which we are learning is about advanced data structures and algorithms, and today we are going to begin with a new module which is titled as B trees. So when we talk about B trees, first of all let us try to understand that as an entity what actually this B tree is. So B tree is actually, we can say a type of self-balancing tree. So with this, let's see, now when we say that it's a self-balancing tree, the first thought which comes in our mind that there are various versions of these balanced trees. So we have ABL trees and many others. Then why do we need one more version of these balanced trees? So the first idea here in B trees is all the leaves of the B tree are at the same level, or let us consider a scenario that we want to store a very large index or a very large data in the memory. So memory, as far as we know, is actually kind of limited. So all these kinds of permanent storages or the large data sets are to be stored on the disk, and then they are brought into the memory as and when required. But what is happening here is whenever a disk is to be accessed, it is much slower than the memory access. It is easier to keep all these in memory, but memory is actually kind of, we can say, limited. We have a limited random access memory, so it is better to keep them onto the disk and bring them as and when required inside the memory. Now what is happening here, disk access is actually a very slower process as compared to the memory access. Now here is a mismatch between the speed. What could be the solution? The solution is we need to reduce the number of disk accesses. Now disk accesses, how are we going to reduce the number of disk accesses? That means we can have a tree with large nodes, and a complete node is to be stored inside the disk in a particular block. So one block at a time, when it is going to read, a complete node is going to be stored inside. Complete node will be read from the disk and will be stored inside the memory. So if we have all these large numbers of nodes, and each node is taking one disk access, so we can say yes, we will be able to reduce the number of disk accesses, and this entire node should fit into the memory as well. So that is first of all a scenario in which we will be taking help from the B trees. So for example, we have index structure for large data sets that cannot be stored inside the memory, and if we are going to store them onto the disk, then we need to approach the efficiency solution in a very different, or in a very innovative manner. So for example, assume that a disk is spinning at 3600 RPM. RPM is rotation per minute. So the spinning speed of your disk is 3600 rotation per minute, and one revolution is occurring in 1/60th of a second, or more specifically we can say 16.7 milliseconds. Now one disk access, when we talk about, it is going to take the same times as that of 2 lakh instructions. So 2 lakh instructions are on the one side, and one disk access is on the another side, and they are taking the same time. So for example, we have a rotation, the disk spinning speed, let's say we can have it double. For example, just now we have seen a rotation per minute speed of 3600. Now let us consider the rotation per minute is 7200 for a disk, and then it is going to take 8.33 milliseconds for one revolution. While if we talk about CPU execution speed, then it is going to execute tons of billions instructions per second when I am talking about a gigahertz clock. So it is not only the random access memory whose access is faster as compared to the disk access. If we compare the disk at the time taken by one access in the disk, it is going to be very kind of higher than one instruction one instruction execution of CPU. So disk basically being an input output secondary storage device is very slow as far as access is concerned. So now these slow access can be compensated with the help of these B trees, because B trees will be having large nodes and entire node is going to be read in one disk access. So that means large amount of data is being read in one disk access. How we will be looking here in our upcoming slides of B trees. So for example, now it is not only about the large data which we are going to access, it is also about the kind of balancing thing. So when we talk about a balanced tree, the first idea which is strike in our mind is about AVL tree. So AVL tree, let us say we have an AVL tree and we want to store about 20 million values or 20 million records in that AVL tree. So what will happen with that AVL tree? So AVL tree is actually a binary tree. So binary tree, that means at most it is having 2 children and each node is having only one value. So this situation of 20 million records to be stored inside an AVL tree is going to end up with a very deep binary tree, and if we are going to keep this into a disk, lots of different disk accesses kind of 24 are required, and this is going to take 0.2 seconds. So 0.2 seconds is actually a very we can say high latency, and we want to kind of improve it. So if we talk about an AVL tree or a balanced tree or a binary tree for that matter, we know that we are actually bounded by this log n lower bound, and we cannot improve on the log n lower bound on search for a binary tree. But so binary tree is going to be for that many records, it is going to be a very deep tree. So now what is the solution? The solution is we can have more branches, and thus we are going to reduce the height of the tree. As the branches increases, depth is going to be decreased. So here in case of a binary tree, there can be at most 2 branches. So that is why the height is kind of huge. So if we are going to reduce the height, or if we want to reduce the depth, we can increase the number of branches. Now how are we going to increase the number of branches? That can be done with the help of a B tree. So let us say in B tree we have so as it is named as a tree, it is having some nodes and those connections between parent and child. That is the inherent character of a tree that is going to be there. So each node has between T and 2T children. Now what is this T? T is we can say it is a large number between maybe it could be 1,000 or it could be 2,000. So each node is having 1,000 or 2,000, or we can say till 2,000 it can have any number of children, and we are fetching an entire node from the disk at one point of time. So fetching an entire node from disk at one point of time is going to give you one disk access, because node is completely stored inside the disk. So even in case of an AVL or binary tree, we are going to store the node inside the disk in a single block. There will be so many blocks because that node is actually not dense enough. Here when I am talking about the node, it is going to have so many keys and so many children. So children, it could have anything between T and 2T. What is the significance of this number T? We will be looking into the definitions. So when we talk about a standard definition of a B tree is typically known by its order. So if we talk about B tree of order M, that is going to be an M-way tree. M-way tree, that means a tree where each node may have up to m children. So, this m could be a large number. So, B tree of order m is an M-way tree. That means here each node of B tree may have up to m children. Now, within this m children or within this B tree, if we talk about, there is also a restriction of number of keys in the leaf nodes as well as in the non-leaf nodes, that we will see. So, the number of keys in each non-leaf node is 1 less than the number of its children, and these keys partition the keys in the children in the fashion of a search tree. So, for example, let us say we talk about a binary tree. So, binary tree, we have only one value in the node, and to the left of that node we have, or in terms of binary search tree, if we talk about, to the left of that node all the values which are lesser than that the node, and on the right of the node all the values which are greater than the node. So, here in a single node, if we are going to store multiple keys, then these keys are actually arranged in we can say in a sorted order. Then all the leaves are on the same level. That is also a very, very important point. All the non-leaf nodes except the root. Root is also a non-leaf node, but here that root is an exception. So, all the non-leaf nodes except the root will have at least ceiling of m by 2 children. The root is either a leaf node or it has from 2 to m children. So, that means for the root node, if it is not the leaf node, that means it is not the only node in the tree, it can have 2 children or it can have maximum m children. So, that means root is basically we can say free from the constraints of having number of children and number of keys and so on and so forth. And a leaf node contains no more than m minus 1 keys, and typically we say that this m should be kind of odd. So, I am just defining I am just reiterating all the conditions here. So, a B tree, let us say if this is of order m, that is going to be an M-way tree, which is in this tree number of keys in each non-leaf node is 1 less than the number of its children, and these keys will kind of partition, these keys will partition the children in the fashion of a search tree. That means onto the left the children which are less than the key, and onto the right which are less than the which are greater than the key. All the leaves on the same level, and then all the non-leaf nodes except the root will have at least ceiling of m by 2 children. That means every non-leaf node except the root should be 50% filled. The root is either a leaf node or it can have 2 to m children, and a leaf node contains no more than m minus 1 keys. Now, when we are going to take this in a consolidated manner, let us see, we have a figure here in which we have represented a B tree. The root of the B tree is having only a single value, which is 100. All other non-leaf nodes are having 2 values each, which is 35 and 65 for the first, and then 130 and 180 for the second. So, now if you can see all the if we are considering the second level, all the keys which are less than 100 are on the left side, and all the keys which are left greater than the 100 are on the right side. This goes with every level. So, 35 and 65 are on the left, while 130 and 180 are on the next. Now, then we have, if we see on the left of 35, there is a node in which the 2 keys which are 10 and 20 both less than 35 are stored. Then in between 35 to 65 we have one node which is storing 40 and 50, and on the right side of 65 we have a node which is storing all the values greater than 65, and this similar binary search fashion is going on the right hand side also. So, less than 130, which are 110 and 120, are on the left side of 130. Then in between 130 and 180 we have 140 and 160, and on the right side of 180 we have all those which are greater than 180 or that particular number. So, what is happening? Each node except the root node, now I am not talking about the root node. So, if you can see the middle level nodes or the nodes at level 2, if they are having 2 keys, that means they are having 3 children. So, that means m minus 1 keys are there, then there will be m children. This goes with every non-leaf node, and every non-leaf node must be kind of, we can say, 50% full. Now, what is going to make that 50%? That is the order. So, in order to understand this, let us see one more figure where a B tree of order 5 is being shown. So, when we talk about a B tree of order 5, that means maximum we can have this certain number of keys, then certain number of children. So, if you can see the first node, which is the root node, that is free from the exception of 50% full. Now, we have 6 and 12 as the second level, and here on the right hand side, if you can see, the second level is having 3 keys. So, the node with the 3 keys is having 4 children, and the node with the 2 keys is having 3 children. Each and every children node is also at least half full, which is kind of when we talk about order 5, then this value must be at least 2. Lesser than 2 keys in any non-root node we are not going to accept. That means the keys should we can say or the node should be at least 50% full. And on the left of 6, the third level, we have 1 to 4, in between 6 to 12 we have 7 and 8, and on the right side of the 12 we have 13, 14, 18 and 25. And similarly this goes with 42, 51 and 62 also, which are the keys of the node which is available on the right side of the value root value, which is 26. Now, here these leaf nodes can be identified by we can say the lines within the slanting lines just below the numbers written. So, if you can see, all the leaf nodes are at the same level because of the constraints of the screen or constraints of the we can say space. I have made it like that, and that is why we have categorically marked these leaf nodes. So, the first level is 26, which is having root node. The second level is, the first node is 6 and 12, and the next node is 42, 51 and 62. These are the nodes at the at a common level, and then the 3 children of the node 6 and 12 and the 4 children of the node having 42, 51 and 62 values are actually at the third level. So, if you can kind of just tweak this, or you can expand this particular we can say tree, then this is going to be an order of 25. Now, with order of 5. So, the order of this tree is 5 and it is containing 26 item. Now, imagine a binary tree, if we, or maybe a binary search tree, if we are going to store 26 item, that how many levels it is going to occupy. So, here as a node can have multiple keys, and because of those multiple keys, a node can have the number of children which is 1 greater than the number of keys inside the parent node, we can have a tree with, we can say a large branching factor, and because of that large branching factor, the height of the tree is actually going to be reduced. Now, if we talk about the properties of these binary properties of B trees, again in terms of orders and all those kinds of things, let us revise them once more. So, if we talk about properties of a B tree, so a B tree is first of all defined with an order. So, let us say order M. The previous figure which we have seen was of a B tree of order 5, and now we are talking about, let us say in a general term, let us say a B tree of order M. We are going to define it as an M-way search tree. This search tree is going to satisfy the following properties. First is, all the leaf nodes of a B tree are at the same level. That means they have the same depth, or all the nodes must have same depth, or height of the tree should be kind of equal for both the subtrees, the right subtree and the left subtree of the root. Now, the keys of each node of a B tree should be stored in ascending order. Now, if you can see this particular figure, all the keys in each and every node are stored in case of are stored as per the ascending order. That is also satisfied. Then in a B tree, all the non-leaf nodes except the root nodes should have at least m by 2 children. So, m is the order. So, if we talk about 5, then 5 by 2 children. So, 5 by 2 children is essentially at least 2 children, which is the condition of being half full, and all the nodes except the root nodes should have at least m by 2 minus 1 keys. So, m by 2 children, which is kind of, if there are 3 children, then there can be 2 keys, and the number of keys will be at least 1 less than the number of children. So, it is also happening here. Root node only 1 key, but root node can have many more keys. Here in this particular situation, root node is having 1 key, the 2 children are there, then the left children is having 2 keys, the 3 children of that left node are there. Considering the node with 42, 51 and 62 3 keys, and as a result there are 4 children. So, this is also a property, or we can say a crucial property of your B tree. So, in a B tree, all the non-leaf nodes except the root node obviously should have at least m by 2 children, which is going to be if we take the ceiling, then it is going to be 3 for the order 5, and all the nodes except the root node should have at least m by 2 minus 1 keys, that is at least 2 keys as in the case of order 5. And if the root node is the leaf node, that means if the leaf node, if the root node is the only node in the tree, then it will have no children obviously, and it is going to have at least 1 key. In the similar situation, if the root node is a non-leaf node, earlier we talked about when we root node is a leaf node, at least 1 key should be there. If the root node is a non-leaf node, then it will at least have 2 children and 1 key, as we have just seen in the figure. It was having only 1 key, but there were 2 children, and a non-leaf node with n minus 1 key values should have n non-null children. So, whenever there is a non-leaf node with x number of key values, then it is going to have x plus 1 non-null children. That means the children should not be null. So, this was actually, we can say, the properties of your binary tree, properties of B trees we are looking into. Then if we talk about the minimum height of the B tree that can exist with n number of nodes, and where m is the maximum number of children of a node, then it is going to have log of n plus 1 with base m minus 1. So, that is a very standard expression for the minimum height of the B tree where n is the number of nodes and m is the maximum number of children of a node. So, the minimum height is going to be log of n with base m minus 1, and the maximum height of a B tree with the similar conditions, that is n number of nodes and t is the minimum number of children that a non-root node can have, then at h max, which is the maximum height of this B tree, is going to be log of n with base t plus 12, and t is equals to m divided by 2. So, this is going to be the expression. These are the facts about B trees. In the upcoming lectures, we will be looking on to many of the operations of the B trees, then the applications, advantages, disadvantages of the trees, and how these operations are going to be performed in a B tree. Here in this lecture, we understood what is the need of the B trees, what is the motivation behind creation of these B trees, and what are the we can say what are the basic properties or how a structure of a B tree is going to be arranged. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.